Assalamu alaikum. This is Farah Shabir along with my team members Maryam Niaz Qureshi and Maryam Ashik of BS Chemistry from Fatima Jinnah Women University. The topic we are going to discuss is determination of metals and their oxides through different types of titrations, which may be complexometric titration, acid-base titration, redox titration or precipitation titration. Let's start with the analysis of phosphate rock. Phosphate rock is basically the unprocessed ore which contain different form of apatites, a group of calcium phosphate, iron and phosphorides. And the type of titration which is used for this analysis is ETTA titration, which is complexometric titration and defined as a form of volumetric analysis in which formation of colored complex is used to indicate the endpoint. And indicators are also used. The first structure, which is of sulfosalicylic acid, and the second structure, which is of arsenazole-3, are used for the analysis of calcium and iron, and the solutions of sodium carbonate and triethanolamine are used to maintain the pH required for the analysis. The first step of analysis is the preparation of sample solution. The sample is taken in solid form, so it is first homogenized by common techniques, namely grinding, sieving and riffle splitting. The homogenized sample was then treated with hydrochloric acid and nitric acid, diluted with water, boiled and filtered to remove any kind of impurities present in sample solution. The remaining residue was then fused with sodium carbonate, and the sodium carbonate is used as a pH modifier. The procedure for the analysis of iron is that the diluted sample was taken in Erlenmeyer flask and the ETTA was taken in burette, and the pH of the sample containing analyte was adjusted around 1.5 to 2, and the sulfosalicylic acid was added as an indicator, and the color of solution became violet red, and then the solution was titrated by 0.01 molar ethylene diamine tetraacetic acid, and the end point was indicated when the solution becomes colorless from violet red color. After that, its concentration can be determined by using dilution formula. The procedure for the analysis of calcium is that the sample solution was boiled with 20% triethanolamine to raise its pH to 8 to 9, and then the 4 drops of indicator, which is arsenazole-3, were added and the solutions turned blue. After that, the solution was titrated with 0.05 molar ethylene diamine tetraacetic acid. The wine red color due to the formation of calcium ETTA complex indicates the endpoint. Then comes a determination of cobalt in paint dryers through complexometric titration. Cobalt is the most important and most widely used dryer metal. It is an oxidation catalyst and acts as surface dryer, and its concentration can be determined by utilizing disodium salt of ethylene diamine tetraacetic acid dehydrate. And the first equation shows that the ETTA replaces the indicator from the cobalt indicator complex and forms its own complex with cobalt, which is yellow-pink in color. The procedure of its analysis is very simple. The weigh amount of specimen is taken in Erlenmeyer flask, and 5 ml of glacial acetic acid is added and heated on hot plate with vigorous stirring to dissolve the specimen completely, and then isopropyl alcohol, water and concentrated ammonium hydroxide are added to dilute the solution and to maintain its pH, and then 2 ml of indicator, which is 1,2-pyridiazo-2-naphthol, is added and titrated with standard copper sulfate solution until the end point is indicated, which is blue in color, and after that its concentration can be determined. Then there is analysis of lanthanides and actinides. Lanthanides and actinides are elements with unfilled f orbitals. Lanthanides are metal and actinides are radioactive element. Lanthanides and actinides are extracted through nitric acid, which is strong oxidizing agent, and then separated through ion exchange mechanism. Through an ion exchange process, the resin beads attract lanthanides and actinides from the solution, and then loaded beads are transported to plant where analytes are separated from resin beads by using eluting agent. Resin itself is organic polymer. After that, ammonium acetate is added as a buffer solution to maintain its pH, and xylenol orange is used as an indicator. Then the solutions of lanthanides and actinides are titrated against ethylene diamine tetraacetic acid, and the color change from yellow to violet indicates endpoint, which is due to the formation of complexes of lanthanides and actinides with EDTA.
Okay, this is Mariam Naz Qureshi, and I'm going to proceed with the following topic, that is the analysis of different metal from different titration methods. So, and my concern is regarding to the determination of zinc oxide, aluminum and phosphate pentoxide in phosphate-based glasses, and that is going to be happening by complexometric titration. So first of all, to determine all of these oxides, we have to prepare a sample solution. So what it consists of, it is mainly 5 grams of the dried sample. So we are going to take 0.5 grams of that sample in a watch glass, and then we have to transfer it into the beaker so that we can mix 100 grams of hydrochloric acid, which is dilute in nature, so that it will get dissolved in it. We are going to boil it, and after that, after the cooling, the solution is transferred into the calibrated flask of 250 ml capacity, and we are going to add water in it to increase the volume as well. So for the determination of zinc oxide and the aluminum oxide, what we are going to do is, first of all, we are going to take the stock solution which we have prepared earlier, and 500 milliliter of the conical flask. We are going to neutralize it. Neutralize means that we are going to put ammonia in it so that it will get, the pH will get maintained, and we are going to put the methyl orange indicator into it. Next step is actually the addition of the buffer. 10 ml of the buffer, which is maintained at the pH of 5.3, is added into it, and we are going to boil it. Now, as I talked earlier as well, it is a complexometric titration, so we are going to titrate with the EDTA and using the xylenol orange as an indicator. Next step, we are going to add around 1 gram of the solid sodium fluoride into this solution. We are going to boil the solution for the 5 minutes again, and there is a time for the second titration. So the first one happened here when we added buffer, and after that, but after addition of NaF, we are going to titrate it again with the same solution, but now the 5 ml of the buffer, and again titrated with the EDT, and after that the endpoint is correspond to the aluminum content of the solution. Now, how we are going to determine the zinc and the aluminum oxide in that specific solution? So we are going to calculate the zinc content by subtracting it from the total volume of the aluminum content in there, so that we'll able to get to know about the zinc's concentration. Next is for the pentoxide. So what is going to happen is this procedure is quite different from the earlier ones, because it involves the precipitation of the phosphate by the access of lanthanum solution. So we're going to take the temperature of around 60 to 70 degrees Celsius, and by the method of back titration, we're going to titrate it with EDTA, again complexometric EDTA titration at the buffer of PA 5.3. Zinc and aluminum are being pre-masked, like they are not going to show any activity in this kind of solution. This is only for the phosphate pentoxide. Next thing is, after the titration with EDTA, we are going to determine how much unconsumed lanthanum is present over there by using the xylenol orange as an indicator. So the endpoint is going to show us from it will sharply change into red to yellow, and that a sharp change in the color will going to show us like how much the pentoxide and how much unconsumed lanthanums are present in there. And again, the amount of the pentoxide is the phosphate pentoxide is established from the amount of lanthanum that is consumed. So we are going to again do the same mathematics by subtracting the volume, and we'll get to know about the pentoxide. Next thing is how to determine the copper. The copper determination leads to a very different process, that is a redox titration. So in the redox titration, of course, the same oxidation reduction reactions are going to happen. So one of the most important application of the redox titration is the hydrometallurgy preparation for the determination of copper. So we use 4 categories and 4 different kind of analysis method for determination of copper. The first one is iodometry, in which we are going to use the iodide ion, which are transform into the iodine ions. Next one is a chromatography or chromatometry. Then is a serimetry. Serimetry is actually the involvement of the ferric oxides and the ferric ions. And last one is a permanganometry. That means we are going to use the potassium permanganate ions in them. procedure, we are going to take the iodometric titration of the copper. So if we have any kind of the solution having the copper inside of them, we are going to use the iodometric titration by the things, because the iodometric determination of the copper is a type of the displacement redox reaction, because one ion is going to displace the other ion in this whole process. So the copper the copper ion is going to react with an excess of the potassium iodide in an acidic medium. I'll be talking about it later in the slide. So here is a reaction which the copper sulfate is reacting with the potassium iodide, as I talked here. So it is going to convert into the copper iodide, potassium sulfate, and the iodine is going to be displaced. So next thing happened in the same reaction is actually it is accompanied by the liberation of iodine, which I have talked earlier as well. The iodine is going to be liberated as a free state. So the large excess of potassium iodide is also necessary to minimize the loss of iodine by evaporation from the process, from the solution. So for that process, we are going to react it with the iodine, and free iodine is actually not lost in the presence of. So we will have to convert it into the ions, and that ion had been transformed here by reacting with another iodide. Next thing, the same reaction is continued here as well. So once the reaction is completed, the iodine produced in that is titrated with the sodium thiosulfate. So titration is actually happening here for the determination of the iodine which is present inside of the solution. The endpoint we are going to see is actually the change of the color by the Stauch indicator, and the amount of the sodium thiosulfate solution required to titrate the liberate iodine is equivalent to the amount of copper. Like the amount of copper is equivalent to the liberated iodine. So we have to determine this thing as well. So here in this picture you can see the Stauch test. The color is changing sharply here. So the sharp change in color by the Stauch test. Here is the reaction which the iodine is reacting, and here is the complete reaction with the reaction proceeds. Next thing is for fluoride for the determination of copper. So first thing we have talked about the iodine. Next, fluoride can also be used for the determination of the copper. So for this, the first thing is by addition of NaF for the ferric masking, because we are not for the ferric masking is essential because we are not going to determine the ferric anymore. We are doing this reaction with the copper, so we have to add any kind of the masking solution so that the ferric will not introduce inside of the reaction or the products. So excess of potassium iodide is added and the mixture is shaken vigorously. That shake will mix all the contents together, and after about 10 minutes the solution becomes deep brown in color. So the same thing is going to happen. The solution from yellowish color turned into the deep brown colors. Next thing, the mixture is then titrated with standard thiosulfate solution until the slurry has a light yellow tint. So after the titration with the thiosulfate, the slurry, the solution will turn into the yellow color, and at this step we are going to put around 1 milliliter of Stauch indicator, and titration must be continued until the mixture turns into the white. So this is actually the whole process in which the white contents are actually determining how much the copper is present in there.
Assalamu alaikum. My name is Maryam Ashik. So first of all, I am going to discuss about the determination of antimony and arsenic by redox titration. The reaction between antimony and arsenic with potassium bromate is to determine the polarity, and the indicator used in this determination is xylidine Ponsau. The chemical formula is C18H16N2O7 and S2, and the structure of xylidine Ponsau is shown in the image, as you can see. For this determination, oxidation reduction titrations are used. For this, first we have to take the hydrochloric acid, and then we'll add the 2 drops of indicator, that is xylidine Ponsau, in it. Then we will titrate the solution with standard potassium bromate with continuous stirring, and as the endpoint approaches, we will add the bromated solution dropwise with 2 to 3 seconds of intervals until the solution is colorless or pale yellow. When the color of the indicator fades, we will add another drop of the indicator solution in it, and then the immediate discharge of the color indicates that the equivalence point has been passed and the titration is of little value. Next is the determination of mercury in mercury salt. The reagents used in this determination are phosphoric acid, hydrochloric acid, water, potassium iodide and mercury chloride. Here are the reactions. In first reaction, mercuric chloride will react with phosphorus acid and water and form mercurous chloride, hydrochloric acid and phosphoric acid. In second reaction, an iodate ion will react with mercurous chloride along with 6H plus and 13Cl- and reacts to form iodine monochloride. Basically, iodine monochloride is an interhalogen compound. It is a red-brown chemical compound that melts near the room temperature. Because of the differences in the electronegativity of the iodine and chloride, this molecule is highly polar and behaves as a source of I+. The process for this determination goes like that. First we have to weigh out 2.5 gram of finely powdered mercury chloride and dissolve it in 100 ml of water in a flask. Then we will transfer the mix to a conical flask and add 25 ml of water and 2 ml of hydrochloric acid and a cess of phosphoric acid solution in it. Then we will stir the solution and will allow it to stand for 12 hours or more. Then we will filter the precipitated mercury chloride and will wash it with cold water. Then we will transfer the precipitate to 250 ml reagent bottle and will add 50 ml of concentrated hydrochloric acid and 20 ml of water in it. We will titrate the mix with standard potassium iodide solution, and as a result, the amount of mercury chloride precipitate titrated will be equal to the volume of potassium iodide used. The next is the aluminium in antiperspirants, that is complexometric titrations. It's a validation for accuracy of flow injection method. The procedure goes like: EDTA and aluminium are allowed to react in a hot solution for several minutes. The excess of EDTA can be fast and easily titrated with zinc plus 2. Here are the reactions taking place during the titration. The endpoint detection, that is the precipitation of the zinc ferrocyanide, appear bluish grey in color. Here is the schematic display of the FI arrangement used. At A is the peristaltic pump, at B is the injection valve, and at C is the reaction coil, or we can also say it as a reactor. Basically, flow injection method was discovered by Ruzicka and Hansen. Flow injection method is an approach to chemical analysis. Basically, it is accomplished by injecting a plug of sample into a flowing carrier stream. And the principle is similar to that of the segmented flow analysis, but no air is injected into the sample or reagent streams. Flow injection method has been used to analyze a wide variety of samples, including environmental, agricultural, clinical, industrial, and pharmaceutical samples. And the majority of the analysis involve the environmental and clinical samples. The advantages of the flow injection method are that it reduces the volume of the reagent and sample. It reduces the volume of waste that could be polluting, and it increases the diffusion of the sample into the stream of the reagent. The last is the determination of sulfide in hydrogen sulfide. The reaction goes like: H2S will react with I2 and form 2H plus 2I minus and sulfur. The titrant for this determination will be the sulfide solution, which must be very dilute, and the concentration shouldn't be greater than 0.01 or 0.04%. The solution more than 0.01 m will have a chance of impurities. The titrant used in this determination will be the excess of acidified 0.005 or 0.05 m iodine solution. The process for this determination goes like: we have to prepare a standard solution of hydrogen sulfide by bubbling the gas to the distilled water. Then we have to place the 50 ml of standard 0.05 m sodium arsenate in 250 ml of flask, and we have to add 20 ml of hydrogen sulfide and hydrochloric acid to render the solution distinctly acidic. We will see a yellow precipitate of arsenic 3 sulfide will be formed, but the solution itself will be colorless. Then we have to make up to the mark with distilled water and shake it thoroughly. Then we will filter the mixture through a dry filter paper into a dry vessel, and we will remove the filtrate and neutralize it with sodium hydrogen carbonate and titrate with standard iodine to the first blue color with starch. As a result, the quantity of the residual arsenic oxide is then determined and deducted from the original 50 ml employed. It equals the concentration of sulfide present according to stoichiometric calculations. That's all from my side. Thank you.